Hello everyone, welcome back to another review video on AP Calculus, Unit 5. This is analytical application of differentiation. So first, let's talk about mean value theorem. So if there's a function f such that it's continuous in the closed interval ab and differentiable in open interval ab, then there is a number c that a is less than c less than b, and f prime of c is the average rate of change over that interval. So what it means is that if a function is continuous and differentiable, and there must be one point c that the derivative is equal to the average rate of change over that interval. Make sure it's continuous and differentiable. So let's look at an example. For the function x squared minus 2x plus c, can use MVT to prove that there's a derivative of -2 over the interval -1 to 1. If so, find the value of x that has the derivative of -2. So this f of x here is a quadratic function, meaning that it's differentiable and continuous over its domain. So over this -1 to 1 interval, it must be differentiable and continuous. So MVT apply here. So let's find the average rate of change. So the average, if you recall, it's the change in y over change in x. So it's f of 1 minus f of -1 over 1 minus -1. So if you substitute 1 in f of x, that will give you 1 minus 2 plus 3. And you minus, if you substitute -1 in, that's 1 plus 2 plus 3, and all over 2. So that is that is 2 minus 6 over 2, which is equal to -2. So based on the mean value theorem, that this average rate of change is equal to -2. Based on the mean value theorem, there must be one point such that the derivative is equal to -2 over this interval. And it's asking for that there's derivative of -2, so there is. And let's find the value that has derivative of -2. So let's take f prime of x. That's equal to 2x minus 2. And so we add it to -2. -2 is equal to 2x minus 2. So 2x equal to 0. So x is equal to 0. So at x equal to 0, the derivative is equal to -2. Okay, let's look at the next theorem. It's the extreme value theorem. If f of x is continuous over the interval, closed interval ab, there are two numbers c and d such that a is less than c and d is less than b, and f of c is an absolute maximum and f of d is an absolute minimum for the function. So what it means is a function is continuous over that interval. There must be a global maximum and global minimum over that interval. And let's look at another concept. It's the critical point. It occurs at point c that the function f of x, where f of c exists and f prime of c is equal to 0 or prime of c is undefined. It's extremely useful when you are finding extremas. The critical points give you all the relative extremas, but it can also give you extraneous extrema points. For example, f of x is equal to x cubed at x equal to 0. F prime of x is equal to 0. But this is not an extrema point. But a critical point, it gives you all the extremas. But you have to identify if they are extrema or they're extraneous. Okay, increasing and decreasing interval. An increasing interval, when an interval with a positive derivative for all points in that interval. And decreasing interval is when every point in an interval with a negative derivative. So let's look at an example here. Find the increasing and decreasing interval of function f of x equal to 2x cubed plus 7x squared plus 4x minus 5. Let's see the graph here. It looks something like this. By looking at the graph, we can analyze that around to this point, that's x is less than -2, then it's increasing. And to here, this interval here, I would say it's from -2 to -0.5. That is decreasing. And over this interval here, so that's -0.5 is less than x is less than infinity. Over this interval, the function is increasing. But we can actually use calculus to determine which interval is decreasing or increasing. So let's see. So let's take the derivative of this function. So f prime of x is equal to 6x squared plus 14x plus 4. And what we're going to do is we're going to find all the turning points, which means that we are finding the critical points. And it's only this point and this point determines if it switched to another interval, another decreasing or increasing interval. So let's find the critical points. We see that this is also a polynomial function, so it must be continuous and differentiable over its domain. So we can just find the 0 critical points. So let's set it to 0, x squared plus 14x plus 4. So let's divide by 2 by both sides. So 0 is equal to 3x squared plus 7x plus 2. We can factor this function. So x plus 2 times 3x plus 1 is equal to 0. So x equal to -2 or x equal to -1/3. So these are the relative extremas we can see on the graph. See, this is actually not -0.5, it's -1/3. That's the powerful tool of calculus. And let's see over what interval is the function increasing or decreasing. So what we're going to do, I'm going to create a graph here. It has 2 points, -2 and -1/3. We're going to analyze all 3 intervals and see if the derivative is positive or negative. So let's say a random number that's less than -2. Let's say it's -3. F of -3 is equal to f prime of -3. 6 times -3 squared plus 14 times -3 plus 4, which equal to 16. So, which means that over this interval, the derivative is positive, which means that at x is less than -2, it's increasing. And let's choose a point between -2 and -1/3. See if this interval is increasing or decreasing. So let's choose f prime of -1. It seems like an easy number to calculate. So 6 of -1 squared plus 14 is -1 plus 4, which equal to -4. Which means that over -2 to -1/3, the derivative is negative, which means that the function is decreasing. So over this interval, -2 to -1/3, decreasing. And let's look at above -1/3. Let's use 0. 0 is really easy to calculate. F prime 0. 0 is just 4. So this is positive, which means that x greater than -1/3, -1/3, it's increasing. And we now successfully use calculus to determine the interval increasing and decreasing, which is more accurate than just guess using the graph. Okay, let's see the next concept, finding extremas. So one, you should find all the critical points over that interval. Then if the derivative went from negative to positive, then it's a relative minimum. And if the derivative went to positive to negative, then it's a relative maximum. And to find the absolute extrema, you should first use the extreme value theorem to make sure that there is a absolute extrema. And then we compare all the values of the critical points and compare all the endpoints of interval, because the endpoints may be the absolute extremas. Then we're gonna compare then we're gonna compare all the values. So let's look at an example here. For the function f of x equal to x cubed plus 2x squared over the interval x is element of negative 2 to 1/2, find all the absolute maximum and absolute minimums. So this is also a polynomial. So which means that it's continuous and differentiable. So EVT applies. So it means that there must be an absolute extrema over the interval. So first we should find all the critical points. To find a critical point, we need to find a derivative. So f prime of x, that's equal to 3x squared plus 4x. And since it's a polynomial, we can just set it to 0 for the derivative. Don't need to worry about undefined. 0 equal to 3x squared plus 4x. We can factor this, so that's x times 3x plus 4, which is equal to 0, or x equal to 0, or x equal to negative 4/3. So these are the possible critical points. And now let's find the values for these critical points and also the endpoints. So our candidate for absolute extremas are f of negative 2, f of, let's see, negative 4/3, f of 0, and f of 1/2. So f of negative 2, which is negative 2 cubed plus 2 times negative 2 squared, this is equal to 0. And for negative 4/3 is equal to negative 4/3 cubed plus 2 times negative 4/3 squared. That is equal to 32 over 27, which is approximately equal to 1.19. Let's find f of 0. So that's equal to 0 cubed plus 2 times 0 squared, which is equal to 0. And f of 1/2 is equal to 1/2 cubed plus 2 times 1/2 squared. So that's 5 over 8, which is approximately equal to 0.625. We see here, we don't really need to determine if the critical points are extremas because we already listed all the values, and we can use these values to determine if they are extremas. So in this case, f of 0 is the lowest point between f of negative 4/3 and f of 1/2, so it must be an extrema, and same thing for f of negative 4/3. So let's compare all the values. For the most positive value, we see is f of negative 4/3. So f of negative 4/3 is a absolute maximum. And the lowest point is actually f of negative 2 and f of 0. So we can say f of 0 and f of negative 2 are absolute minimum. And now let's look at another concept, concavity. If a function has a positive second derivative, which the slope is increasing, then it's concave up with an U shape. If a function has a negative second derivative, then it's concave down with a downward U shape. An inflection point is when the second derivative equals 0, where it changes concavity. So a function has a positive second derivative, it looks something like this. It's going down and it's going up, 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 where the slope is increasing overall. So if you draw a f prime and x, it will look something like this for this graph. And for this one, it's concave down because it's decreasing its slope. At first, the slope is positive and it turns to negative slope. So it has a negative second derivative, which is concave down with a downward U shape. An inflection point is basically changing concavity. So we see here at x equal to 0, it's changing from concave downward to concave upward. And here's the relationship between f of x, f prime of x, and f prime prime of x. This whole function here, we see the first derivative, which is the purple, it's decreasing. It's from positive going more and more negative until this inflection point at x equal to 0. It's a turning point for the first derivative, and after that the slope is increasing. And for the second derivative, it just goes from negative to positive. Okay, let's talk about second derivative test. For a critical point, if the second derivative at a point is positive, then it must be a local minimum. And if the second derivative is negative, then it must be a local maximum. If second derivative equal to 0, it's uncertain. It could be a minimum, maximum, or neither. So for the positive second derivative, which is concave upwards, we see it has a minimum point. And for negative second derivative, we see concave downward, it has a relative maximum point. For second derivative equal to 0, we're uncertain if it's a extrema. It could be. Let's say for the function f of x is equal to x to the 4th, the second derivative, which is, let's calculate first derivative first. First derivative is equal to 4x cubed. So second derivative is equal to 12x squared. At x equal to 0, second derivative is equal to 0. However, x to the 4th graph actually looks something like this, where it has a relative minimum. So let's look at an example and to determine if it's a maximum or minimum based on the second derivative test. For this function, f of x is equal to x cubed minus 3x, determine the point of inflection, interval with concavity, and local extremas. So first is to take the derivative. So f prime of x, you can see it's 3x squared minus 3. And let's find the point of inflection first. So which means that we need to take the second derivative, f prime of x, which is equal to 6x. And the point of inflection, which is when second derivative is equal to 0. So we let it equal to 0, so which x equal to 0. That's the point of inflection, where it changed the concavity of inflection. An interval of concavity. We see there's two choices, x is less than 0 or x is greater than 0. Let's substitute some value. for the second derivative. Let's say f prime prime of 1, which equals 6, if we substitute in, which means that it's concave upward. Concave upward. And for, this should be x greater than 0. For x less than 0, let's do f prime prime of -1, which is equal to -6, which means that it's concave downward. So over x is less than 0, it's concave downward, which means that it has a maximum. For x is greater than 0, it's concave upward, so which means that it has a minimum. So now let's find the critical points. We see f prime of x equal to 3x squared minus 3. Let's set it to 0 because this is a polynomial. 0 equal to 3x squared minus 3. So 0 equal to x squared minus 1. So x equal to plus or minus 1. And for x equal to 1, we see it's greater than 0, so it must be a minimum. For x equal to -1, it's less than 0, so it must be a minimum. And that is the solution for this problem here. So next one, we will sketch graph using derivative. To sketch a graph, first find the first and second derivative function and plot all the critical points. And we will plot all the inflection point. And with concave upward, we just draw a U-shape to connect the inflection point while it's contacting the extremas. And same for the concave downward, but with a downward U-shape. So first, we should take the first and second derivative. So f prime of x, which is equal to 3x squared plus 2x minus 1. And f prime prime of x, which is equal to 6x plus 2. So let's find the critical points. This is also an polynomial function, so we set it to 0. 0 equal to 3x squared plus 2x minus 1. And we can factor this, so that's x plus 1 times 3x minus 1, which is equal to 0. So x equal to -1, or x is equal to 1/3. And let's plot this value, but first let's find the value of these points. So f of -1 is equal to -1 cubed plus -1 squared minus -1. That's -1 plus 1 plus 1, which is equal to 1. So we have to plot -1, 1. -1, 1 at this point here. Let's find f of 1/3. That's equal to 1/3 cubed plus 1/3 squared minus 1/3, which is equal to 1/27 plus 1/9 minus 1/3. So that's -5/27, which that's approximately equal to -0.185. So we should plot 0.33, which that's the approximate value for 1/3, and -0.185, the critical point. So -1/3, it should be around here, and -185 should be around here, say. So those are the extrema points, and let's find the point of inflection. So we should set the second derivative equal to 0. The second derivative function is 6x plus 2. So x is equal to negative 1/3. So let's find f prime. Actually, let's find f of negative 1/3. F of negative 1/3. That's equal to negative 1/3 cubed plus negative 1/3 squared minus negative 1/3. That's negative 1/27 plus 1/9 plus 1/3. That is approximately, that's equal to 11/27, which is approximately equal to 0.407. So we will plot negative 0.33, 0.407. That's around, I would say it's around here. It's approximately here. So the function is concave up. Actually, I plotted it wrong. It should be around here. Around here. Around here. And the concave up interval is, we see this graph here, it looks something like this. So when it's concave up, the value, it must be positive. The value of this is like this part here. So we can say x is element of negative 1/3 to infinity. Basically, the right-hand side is concave up, and concave down is x is an element of negative infinity to negative 1/3. When it's, so let's see. We have all these informations. We can plot the function, and it says is this function, so we can find the endpoints. X approaches negative infinity, which is equal to negative infinity, and limit x approaches infinity, which is equal to infinity. So we got all these points, and the information can plot this. So what's happening here is that it's having a downward U-shape and until this critical point here, and it's U-shape until this point here, where it has it's a turning point for the concavity, which now we should draw a U-shape upward. And the graph looks something like this. And now let's talk about connecting a function with its derivatives. So here's some calculus-based justifications. The correct answer must have some calculus in there, whether indicating that f prime is positive. And even the correct interpretation, but with no calculus, is still incorrect. So here's some calculus-based justification. F of x increasing when f prime of x is positive. F of x is decreasing when f of x is negative. F of x has a minimum point when f changes sign from negative to positive, where f prime of x is greater than 0. f of x has a maximum point when f prime of x changes sign from positive to negative, or f prime of x is less than 0. F of x has an inflection point when f prime of x changes sign, and f of x concave down when f prime of x is less than 0. And there's type of question was asking you to match f and f prime prime. So draw the derivative of each and find the derivative match to which graph. If there's no match, then it's f prime prime. If there's a graph that matches with f prime prime, it's f prime. And the last one is just f. And now, this optimization problem. This problem where you have constraints and you have to calculate the max or minimum. So here's some tips for you. So first, you should read the problem carefully. Make sure to read it multiple times and draw a diagram of the question. If you misread the question, you certainly will get it wrong. And next, list the given some constraints. And for almost every problem, you have a fixed value. For example, a value is constant. Then solve everything in terms of one variable. If it involves two or more variables, solve in terms of one variable. Then take the derivative of the function and find the critical points, and you need to identify if they're maximum or minimum that the question is asking, and use the second derivative test and find the endpoint of the interval to make sure that the endpoint is the result. And you should practice, and practice. This type of problem you should do all type and get familiar with it. So let's look at this problem. A volume of cylinder equal to v cubic meters, where v is a constant. So that's our constraint. V must be a constant. Find the proportion of radius and height of the cylinder that minimize the total surface area. So what it is, let's say we have a cylinder here. Let's try better. Say we have a cylinder here that has a total volume v, and that we need to find the radius and height such that it has the minimum surface area. So let's list the equations that's relative to this. So it says the volume must be equal to v. So volume, what is volume? That's equal to pi r squared at h. And it's also asking for the surface area, so we also need to list the equation for surface area, which is 2 pi r squared plus 2 pi rh, 2 pi rh. Now, S is in terms of both r and h. We need to solve in terms of one variable. So we see h only appear once. So let's solve h in terms of r. So let's use the first equation, h, which is equal to v over pi r squared. Substitute back into s. We get s is equal to 2 pi r squared plus 2 pi r times v over pi r squared. Pi cancel out. One of the r cancel out. So s is equal to 2 pi r squared plus 2v over r. And now we can take the derivative of this solved equation because it's telling us to minimize the total surface area. ds, let's just do s prime. Just do s prime is equal to, let's see, 4 pi r plus, it should be minus 2v r -2, which is equal to 4 pi r minus 2v over r squared. And let's solve for the critical points, which this whole expression equals 0. So 2v over r squared equal to 4 pi r. And we need to, let's see, 2v is equal to 4 pi r cubed. So we get v is equal to 2 pi r cubed. Now we already solved for v. V is pi squared h. So pi r squared h, it must be equal to 2 pi r cubed. So we can say that h is equal to the pi cancel out, 2 of the r cancel out, so that's 2r, which means that the height is equal to the diameter of the base. Then it will have the minimum total surface area. The last one is the behavior of implicit relation. So for the given implicit equation, to determine the critical points, and the same thing as the ordinary functions we saw before, that the critical points occur when dy dx is equal to 0 or it does not exist. So the vertical tangent is meaning that dy dx is equal to undefined, which it has a vertical tangent. The slope must be some number divided by 0. And it must be constrained to a certain x value because the y value cannot change. And for the tangent to y-axis, meaning that the axis must be 0. And for the horizontal tangent, meaning the dy dx equal to 0, it must be constrained to some certain y value, such as y equal to 0. So let's do a problem here. For implicit equation x squared minus y squared minus 5xy is equal to 25, that this is the dy dx. Solve for the x value that x is greater than 0 that has a vertical tangent. So what does it mean? Is that dy dx must be equal to undefined. When is that undefined? When the denominator equal to 0. So we can say 5x plus 2y equal to 0. So we can say that y is equal to negative 5 over 2x. And now we are solved in terms of one variable here. It's asking to solve for the x value, so we need the other variable to be in terms of x. Substituting into the original equation, x squared minus negative 5 over 2 x squared minus 5x times negative 5 over 2x, which it must be equal to 25. Let's see, x squared minus 25 over 4x squared plus 25 over 2x, which is equal to 25. So let's see. 29 over 4 x squared, it must be equal to 25, multiplied by 4 to both sides. So 29x squared must be equal to 100. So x squared equal to 100 over 29. So x is equal to positive or negative 10 over square root of 29. And it's asking for the positive x value, so it just equal to 10 over square root of 29. And using a calculator, we can say that's approximately equal to 1.857. So at x equal to approximately 1.857, it has a on vertical tangent. So thank you for watching my video, and it concludes my review video for AP Calculus Unit 5, and please like and subscribe, and I will see you next time.